Swayamprabha. Digital India. Educated India.
We were discussing about some examples of unsteady flows, and while discussing unsteady flows we first discussed about a classical flow where there was no confinement and there was an oscillating boundary because of which fluid motion was actuated, and that is known as I mean these kinds of problems where the boundary is set into motion or the boundary is set into oscillation. These are classical problems in fluid mechanics. We studied one such problem in detail where the plate was moved suddenly in one particular direction and that allowed the fluid in the vicinity to move in the same direction. So, that was the classical Stokes first problem, and then we discussed about the motivation of studying these kinds of problems which are like shear driven flows, and then we try to figure out that what would be the change in the scenario if there instead of instead of an open environment in one side there is a confinement. That means that you have a plate like this which is moving towards the right, say with a velocity u1, and you have another plate which is stationary and the gap between the two plates is h. When h tends to infinity, then the problem is like the classical Stokes first problem. So, this can be thought of or imagined as a Stokes first problem with confinement, right. It is a modified version of the Stokes first problem, or in terms of the classical Couette flow also it is like a Couette flow. We are it is basically a Couette flow because you have two parallel plates, one plate is moving relative to the other, it is a Couette flow, but we are interested in the unsteady state solution of the Couette flow problem. Now let us try to see that what is the steady state behavior of this. It is well known to all of you, but just to recapitulate. So, the first the governing differential equation for the general flow problem is what? This is consistent with all the assumptions we have discussed in details earlier. Now, before moving on to the steady state solution, what we will do is we will non dimensionalize this problem. So, we define u bar as u by u reference. There is a natural reference velocity scale which is u1, y bar is y by h. Unlike the Stokes classical Stokes first problem, here the natural length scale is h, and then there is a natural time scale. The time scale is a function of the nu and the h. So, that can be worked out by noting that the order of magnitude of this is u reference by t reference, and the order of magnitude of this is nu u reference by h square. Since these two terms are of the same order, then t reference this implies that t reference is equal to h square by nu. So, you can define accordingly one T bar is equal to T by T reference, where T reference is h square by nu. So, what is this h square by nu? H square by nu is the characteristic time by which this characteristic change diffuses over a distance h. That characteristic, this what creates the characteristic change? The motion of the boundary at the bottom creates the characteristic change, and that motion gets propagated into the fluid because of viscous effects, and the characteristic time that it takes to get transmitted up to a distance h is h square by nu. So, that is the characteristic time scale based on h as a characteristic length scale. So, with all these, now a big question comes that why are we taking h as a characteristic length scale, right. So, we are taking it with a very important assumption, and the assumption is that this h is smaller than, like if you are considering that instead of h there is a y reference, then T reference scales with y reference square by nu. That means y reference is of the order of square root of nu T reference, right. If instead of h it is y reference, something arbitrary. Now, we are considering the characteristic time scales to be such that this corresponding y reference is of the order of h. If the corresponding y reference is much less than h, that means this plate is like as if like at infinity. That is not the case which is of interest to us, because then the situation will boil down to the Stokes first problem. In fact, I will ask you to work out a homework where you have to show that under what limiting conditions the solution of this problem boils down to the solution of the Stokes first problem effectively, but that you can do after we complete the solution of this problem. So, the understanding is pretty clear that our reference time scale is not such that this y reference is much less than h, and that in fact the case that we are considering that h is very small, so that with a little bit of like time elapsed this will come to the order of h, because it is a micro channel or a nano channel that we are considering, that will be the practical scenario. So, our assumption of y reference is equal to h is not obvious, you have to keep in mind, is not obvious, but very practical from the consideration of many microfluidics and nanofluidic scenarios. So, with that assumption your governing differential equation will be now we are interested to get the unsteady part of the solution. So, we will separate that out from the steady part of the solution. So, let USS be the steady state solution to this problem. So, what is USS? USS bar means non-dimensional steady state version of the solution to this problem. So, the steady state version of the solution to this problem will be governed by this equation with the unsteady term equal to 0, same equation, but with unsteady term equal to 0. So, if we put the unsteady term equal to 0, then this, if we integrate it twice, this is what we get at the solution. The boundary condition at y is equal to 0, see the steady state boundary conditions should be the actual boundary conditions. Why? You might argue that I will dump the actual boundary conditions onto the unsteady state and make the steady state boundary condition something different from the actual boundary condition, but that you cannot. The reason is that the problem will eventually come to a steady state, and when it comes to the steady state, the whatever is the physical boundary condition, that has to be satisfied. So, you have to account for the boundary condition assuming that once the steady state has been attained, that steady state is dictated by the actual boundary conditions which are physical to the problem. So, at y equal to 0, what is the boundary condition? This is your y axis, USS equal to, what is the boundary condition at y equal to 0? This is 1, and at y equal to 1, non dimensional y equal to 1, what is u? 0. This is no slip boundary, both are no slip boundary condition. So, the solution will be very straightforward, 1 minus y, right. Just plug in C1 and C2, C1 is C2 is 1 and C1 is minus 1. So, this is the steady state solution, and this is the solution typically for the steady state Couette flow that you learn in undergraduate fluid mechanics. You have two parallel plates, one plate moves relative to the other with a velocity, you have a linear velocity profile in between, if the velocity profile is translationally invariant along the x axis, that is a function of y only. Now, the interesting part, what is the unsteady part of the solution? See, we have to keep in mind that many problems we solve at steady state, many problems we solve at unsteady state. In the world, no problem is actually a steady state problem, because you think about a situation like say there is a water in a channel. Now, there is some condition which makes it start from rest, maybe there is a pressure gradient that is applied at time equal to 0, or maybe there is a shear that is applied at time equal to 0, maybe there is a electrical field that is applied at time equal to 0, whatever, something is applied that creates a disturbance, and there is a time that the system takes to adjust to the disturbance to come to a steady state, that is the response time of the system. Typically, if the response time of the system is much shorter than the characteristic time scale, let us say that the characteristic time scale over which you are doing an experiment is hours, and the response time is a few milliseconds, that within a few milliseconds it reaches the steady state, then we are mostly interested about the steady state solution, we do not care about the unsteadiness. But if the characteristic time scale over which you are doing the experiment is comparable with this time scale over which the system takes its time to relax or to come to adjust to the change, then the unsteadiness of the solution is important, and you have to look into the unsteadiness of the solution. So, this is what I wanted to discuss very carefully, because see in the class when we are giving lectures we are solving some problem as steady problem, some problem an unsteady problem. In engineering, when you are solving a problem, no problem in the real world is posed as steady or unsteady. You have to give your judgment that whether your unsteady part of the solution is important or your unsteady part of the solution is not important over the time domain that you are considering, and only the steady state solution is important, provided that the system attains a steady state. If the system never attains a steady state, that means it attains a steady state only at t tends to infinity, that is a very special case that we are not considering here. Now, we are interested about the unsteady part of the solution. So, what we are writing is we are writing the total solution we are decomposing into a steady part and an unsteady part. How can we make this decomposition? We can make this decomposition because eventually if a steady state is attained, the unsteady part should be 0 and there will be a steady state solution. So, the unsteady solution should be decoupled from the steady state solution. So, then you can write here u steady state we have already solved, the solution is 1 minus y bar. We will keep this in mind, we will make use of this whenever we are going through the mathematical part of the solution. So, you can see that the time derivative of u bar is same as time derivative of u hat, because this is a function of position only, this is not a function of time. Not only that, the second order spatial derivative of u bar is same as second order spatial derivative of u hat. The reason is that u steady state, although is a function of y, its second derivative with respect to y is 0. So, that means the unsteady state governing equation remains same if we write it in terms of the unsteady part of the solution. Boundary conditions, at y equal to 0, what is u hat? At y equal to 0, u is equal to u steady state, right. So, u hat must be 0, and similarly at y equal to 1 also u hat equal to 0. This is for time greater than 0. And initial condition is everything is stagnant at time equal to 0. So, you can see that by decoupling the steady state solution from the unsteady solution, we have achieved another interesting feat. What is that? We have made all the boundary conditions homogeneous. So, that is a mathematical way of looking into the scenario, but that is what it has made. See, had we considered the complete solution, for the complete solution the boundary condition at y equal to 0 is not homogeneous, but for the unsteady part of the solution the boundary condition at y equal to 0 is homogeneous, that is at u hat is equal to 0 at y equal to 0. Now, because of this nice homogeneity in the boundary conditions, we can use the separation of variables. So, let us write u hat as a function of y into a function of time, right, that is the method of separation of variables. So, its time derivative is f into g dash, right, and second order spatial derivative f double dash into g. So, if you substitute that in the governing equation, you will get f g dash is equal to f double dash g. So, f double dash by f is equal to g dash by g. Question is, so this is I mean by this time you have now appreciated that why we are interested to write it in this way. This is a function of y only, this is a function of t only. That means we claim that each is equal to a constant. Now, what constant? Positive constant or negative constant? It is a negative constant, minus lambda square say. Now, why are we interested to, or why are we writing this as a negative constant? The reason is pretty clear, like when you write dg dt by g is equal to something, this will give a exponential solution of g as a function of time. If there is eventually a steady state solution, then the unsteady state solution should decay exponentially with time, so that at t tends to infinity the unsteady state solution will be 0 and you will get the steady state solution. So, that means there must be an exponential decay. So, the coefficient coming with the exponentiation at the top, that should be a negative constant, so that it is a decay and not a rise. That is why this minus lambda square. So, let us complete this. One by g dg dt is equal to minus lambda square. So, ln g is equal to minus lambda square t plus ln C1. So, g is equal to C1 e to the power minus lambda square t, t means this is non dimensional time, t bar. I have used C1 before for this problem, okay, then C1 C2 we have already used before. So, C3. So, g is equal to C3 e to the power minus lambda square t. Then the functions of y. So, f double dash plus lambda square f is equal to 0. So, what is the solution of this in terms of sine and cos, right? So, f is equal to C4 cos lambda y plus C5 sin lambda y, y means y bar. Now, let us apply the boundary conditions. At y equal to 0, u equal to 0. So, boundary condition number 1, at y equal to 0, u equal, not u, u hat basically, u hat equal to 0 means f is equal to 0. So, f is equal to 0 at y equal to 0 means C4 must be equal to 0. And boundary condition 2, at y is equal to 1, u hat equal to 0, right. So, sin lambda equal to 0, right, and that means lambda is equal to n pi. I just want to reiterate that instead of sin lambda is equal to 0, had we considered C5 equal to 0, that would also have satisfied this boundary condition, but that would have given rise to a trivial solution that u hat equal to 0. So, here we are seeking values of lambda that will give us non trivial solution for this problem, and that makes it an eigenvalue problem. Okay. So, how many such possible values of lambda are there? There are infinite number of such possible values of lambda. So, we call this lambda n, lambda with subscript n, which is equal to n pi. Now, let us write the solution. U hat is equal to f into g. F is C4 sorry C5 into sin lambda y, and g is C3 to the power lambda square minus lambda square t. So, C5 C3 to the power minus lambda n square t into sin lambda n sin lambda n y. And because, so first we can replace this C5 C3 with a constant or just a name a and give it a subscript n, because that constant is different for different n's, and because it is a linear problem, the resultant solution is a linear superposition of solution for all possible values of n, that makes it sigma n e to the power minus lambda n square t sin lambda n y. How do we find out n? That is the only question that remains to be addressed to solve this problem. For that we have to use the initial condition. We have not yet used the initial condition, right. This kind of problem is called as initial boundary value problem. That means it has an initial condition and it also has boundary conditions. So, we have used the boundary conditions, but we have not yet used the initial conditions. Now, to find an, see we have to somehow bring down this series to a single term, and that may be possible. So, this is f n by using the orthogonality of f n. So, we now have to derive the orthogonality condition for f n. I have already discussed how to derive the orthogonality condition in the context of one problem earlier, and we will use a similar technique, and we will try to do it little bit faster than before, because we have already discussed the principle. So, the eigenfunction for the eigenfunction f n is given by this equation, which is d2 f n dn2 plus lambda n square f n is equal to 0. What we do is we multiply this by f m and integrate it by parts. Sorry, dy. Sorry. So, we multiply this and integrate it by parts from y is equal to 0 to y is equal to 1. With f m as the first function